Hi everyone, I'm Aleksandra Faust, and I'm going to talk to you today about self-supervision in motion planning. Here's an overview of several examples of a slightly different take on the motion planning, largely motivated by the fact that the way we think about the robotics and what we're asking about the robots and so on had changed over time. So one thing that we're really interested in, where there's a huge potential in robotics, is really autonomous robotics at scale in real world on real robots, which means going over several different number of different environments and so on. So let's look at the example. This is an example of real world. We have a robot here starting in one point, and we wanted to drive to the sink here in this micro kitchen. And we just kind of did the same task over and over again, letting things change. And this is the real world. Now there is a guy here sitting, the standing in a way. There's another person going in, and the robot needs to be able to adapt and adopt its plan and so on as it proceeds. Now there are people standing around, and we did not make this up. Here's the janitor coming in. So the robot needs to safely work in this ever-changing real world. This is, by the way, fully learned reinforcement learning policy. The robot is taking its LiDAR sensor observations and outputs the linear and angular velocity to get to the point. So this is what we mean by real world. Next, it made it. Oops. Next, robots come in all kinds of shapes and sizes. And what they can do, what they're capable of doing, or the way they're able to complete the task going from A to B, it really depends on their sensors and their dynamics and their shape of their bodies and onboard compute and so on. And for all of them, we want to get them to go from A to B in safely and feasibly according to their capabilities. Even some simple fetch and freight here, same kinematic model. The fact that freight does not have the body makes it 100 pounds lighter. And that makes a huge difference in how fast it moves and so on. They have the different sensors and so on. So when we say real robots, we need to have the same learning methods, or generally methods, that work for a wide variety of the robots. And we should also kind of take that they're never perfect, right? Even if we have a good control policy and so on, the fact that there is a hardware imperfections and so on, they're never ever going to be perfectly executed. And we need to take that into account. So how do we classically approach this? Classically, we have the observations, and then perceptions, and SLAM takes that and produces the SLAM and maybe obstacle map or occupancy grid or so on. Motion planning takes that, outputs the sub goals, and there goes then control that takes the goal and kind of computes a trajectory or whatnot. And then we put that on the robot and we hope for the best. And I hope carries a lot of weight here. This is generally good because it's a separation of concerns and so on. But what happens in the practice is that things start breaking at the seams. We put on a robot does not quite work out, and we cannot look at where it's kind of things broken and so on. It is essentially an open loop system because the motion planning does not know what the shortcomings of perceptions are. Controls don't know what the shortcomings of the planning are. And then once we kind of put in a robot, the planning does not know what happened in reality, what worked when didn't work. We put an engineer there that basically collects that experience and says, aha, we shall fix this. So open loop here is the problem, or the fact that it's engineering the loop. And the second problem why this generally does not scale across number of environments and so on is that we treat every instance of a problem as a new, more or less, in the classic approach. And we do not look into the fact that the environments have some structure in it, that their problems are similar and so on. Typically, we kind of fix on a single environment or maybe a small set of the environments, and we kind of go with that, and then we tune all the bugs, fix all the bugs on these kind of scenes specifically. And then we move to the next one. There's a whole new set of heuristics and whatnot that is being kind of human engineered So can we do better? If we kind of just look for the biological systems for inspiration, biological systems, whatever they do, they take the world with their sensors and their output or express themselves, let's say with emotion. There is a language and whatnot, but let's just for the argument's sake, stick to the motion here. And anything that comes into box kind of happens in between these pieces. And then general evolution determines the system characteristics that are fitting into the environment and the task that the system will be system will be solving. Then we go and practice. This is my daughter practices walking. We interact with the environment and we learn some basic skills that we're not perfect at. And then once we have skills, we develop intuition. and intuition is nothing other than ability to reflect on our previous experience and develop a sense of predictive model, if you wish, of how successful we will be in the future performing similar tasks and so on. And then basically this reflection helps us estimate our abilities without executing the task. You don't need to try walking on a rope to know that that's a difficult thing, right? Because you've tried similar things and so on in the past. So the question here is, can we use and borrow some ideas and some inspiration from biological systems to make motion planning specifically and robotics better and more scalable? So the key idea here is that biological systems practice, learn, and improve over time, right? So we have our pipeline that we love and learn. Can we add, let's first add that each kind of layer in this pipeline has access to the raw sensory observations. That way, the motion planning say, oh, okay, thank you, perception. I have your occupancy grid, but now I see the sensing. Well, last time we did that that didn't quite work out. And then the second piece here is to equip the motion planning and controls and others with summary of the previous experiences in other environments and so on, and let them learn these kind of estimates and predictive models that they can use to basically critically assess the planning and the proposed goals and whatnot. Basically, we're closing the loop here. And all layers in this stack operate with the same information. Perception has been doing this for some time now. There is prior work in controls on this talk. I want to focus on motion planning. And basically, just to go back, the separation of concerns is here, that the controller receives the goal and then goes and executes, like we saw in that micro kitchen, deals with whatever needs to be dealt on the way that's kind of due to the real world. But the motion planning is responsible for providing safe and feasible goals under assumption that perception is imperfect and these control policies are imperfect. So what you're gonna get is not exactly what you send it is not exactly what you're gonna get, but you're gonna get feedback on how well that worked in practice. So that's kind of the rough idea. So there's a number of papers that we had recently in this area. I'm gonna go over 4 of them today, just as an example. But the pipeline and the general idea is that we practice first. That lets us collect the data set. So we have some kind of planning that is working-ish. Maybe it's using more expensive method to do that, so it's not as fast as it should be, or maybe it's not as good as it should be. Anyways, it collects a data set. Then we use that data set collection and then we use that model as a heuristic for planning to propose better goals to be sent to the controller. So first, the 4 examples that I want to talk to you about today is learning collision checking. The second one is also in sampling, from the sampling-based planning, is selecting or sampling and prioritizing the nodes in the sampling-based methods. And then the second 2 are in the dynamic environments, one for navigation around humans, visual navigation around humans, and the second one is a kind of multi-agent setting when they're trying to do a cooperative task and meet each other. All right, so let's talk about first about the collision checking. Collision checking is the key component of sampling-based planning. It is the primitive operation that we basically measure the complexity of the sampling-based planning. And here is a rollout of RT here, for example. And one thing that we notice, like this, classically we do this with a computational geometry. It's expensive, it's slow, it's 100% accurate, assuming that the data is being provided, it's accurate. So if we kind of notice here is that really 90% of these or so we're using expensive methods, and lots of these are completely, we don't need to do any of these collision checks. The only really collision checks that matter are along the blue path that we selected. And yes, collision checking takes up to 90% of total computation time in sampling-based planning. Can we do better than that? Can we have a cheaper method that's not accurate, learned, that can kind of get us in a neighborhood, and then we can kind of get better from that? So a couple observations here. Separation distance is learnable. Separation distance measuring basically what's the minimum distance between the robot and the environment. And separation distance depends really only on the poses of all mobile bodies in the environments. So if I know where my arm is and my desk is, if I kind of keep moving it towards that, well, now I'm kind of getting towards the camera, and that's getting into collision, and now I'm kind of moving forward. It's also separation distance is Lipschitz continuous and monotonic, so I'm going towards the edge and I'm moving backwards, right? So that's good. Second observation, neural network actually are very good at processing large batches of data. And you got, by kind of increasing the size of the batch, the time that it takes to process them all does not increase that much. It's easier to verify and repair a partially correct trajectory because it's a smaller sampling-based planning. So even if this was not perfectly correct, we can kind of fix the smaller one. And then neural networks are differentiable, and gradient can be helpful, for example. So kind of between these observations, we set to use the neural networks to learn the separation distance in order to be able to do collision checking. So before that, we first do some foundations. If we're going to use the previous experience, it does not make sense to use to just kind of look at the fixed environment. Because look, in the room, my chair is going to move, right? The monitor is going to move, the desk is going to move, walls will not move. So there is some objects in the environment that the robot is operating that moves between the queries. So we introduced the definition of the workspace configuration space, where actually the workspace itself has some degrees of freedom. Next, we add the robot, and this yields to the extended configuration space. Now we have the robot that moves that we can control, right? And the room or so on the objects that have, and the collision checking depends on that extended configuration space. And finally, we've added the definition of the path planning in the extended configuration space. We basically said that a safe collision space is finding the path in the extended configuration space where we can only control the robot. So how do we go then about learning the separation instance? Here's a picture here. We can basically subsample out of this extended configuration space, different configurations, use our expensive computational geometry methods to compute the clearance between the robot and the objects, and that's how we create a data set. Once we have a data set, we can train the model that takes in as an input the extended configuration point and outputs the estimated separation distance. And if it's above a threshold, then we can say it's outside, it's not in collision. If it's below the threshold, we can say it's in a collision. So let's see how well that works. In terms of on the left side, So we evaluate this on 5 environments that are going between 14 degrees of freedom and 7 degrees, or 30 degrees, 7 to 30 degrees of freedom. And they have different geometries, different. So this one R2D2 has rounded surfaces. The environment with shelves has kind of lots of narrow passages and whatnot. So it kind of covers good, has coverage of the different environments. So on the left side here, we have a graph that says, what is the time per inference to do a collision checking? Using the JJK, which is the computational geometry method, as one would expect, the time to compute is fixed, regardless of how many collision checks we do. But it depends, the time to compute depends on the environment itself. For the neural network that we learn, the time decreases with the number of batches, and we get something like 400 times speed up on batches that are over 1,000 collision checks in a batch. Second thing that we observe here is we look at what is the accuracy of the model, and as one can imagine, with the larger data set size, the model accuracy is going to go up. But what's interesting also that it depends on the degrees of freedom and not on the environment type. And these degrees of freedom is basically, we took all the 5 environments that we said and kind of froze certain pieces of it to be able to. And this actually makes sense. It makes sense that the problems with the fewer degrees of freedom are easier, so we need a smaller data set to reach the accuracy, and problems with the higher degrees of freedom are more difficult, so the targeted sampling and data set size makes sense. This is not what we see with the classic methods that kind of depend just on the geometry of the space. All right, so now that we have our semi-accurate or estimator for collision checking, how do we use it? And we still want some notion, we want to retain the notion of the probabilistic completeness and so on. So we use the clearance net as a collision checker, and we do basically notice that, hey, we can do not just one sample at a time, we can do the whole edge. And not only one edge, why not extend RRT at a bunch of, I think we're doing 5 to 50 edges at the same time, checking the entire edges. And these are batches, which kind of expands it. So yeah, we're doing about 5,000 collision checks in parallel. All right, so that sometimes works. We're lucky, maybe environment is easy and there is not many collisions and so on, so we're good to go. But sometimes we'll kind of end up with a path that is not in collision. So what we do is once we have a proposed path, then it's time to get out the expensive computational geometry method and verify the path. And we continue then doing that and use the gradient to push the boundary outside. If we can't do that, then we basically end up solving a smaller problem and reconnecting it. So how well the method works. The blue line is the proposed method, and it's compared with the standard RT with the computational geometry method, and the fast-run, which is using non-neural networks. It's still learned, but it's using the supported vector machines. And in these two cases, if it's consistent across the environments, we do get faster. I get about 50% motion planning speed up and about 24% more efficient paths. So here is a video of how that looks like. We're asking here, the fetch is fully controlled, it's 15 degrees of freedom. To go in and basically place the gripper between the duck right to the corner. It is near the narrow passage. Now on the next one, we move the shelves and we move the initial pose of the robot. And the goal is to place the gripper on top of duck's head. So the robot actually needs to move here as well. And here we go. All right, so that was one use. Second example is the probabilistic roadmaps and the roadmap planning, we're trying to look into the samples. And just kind of for a brief motivation, the standard PRMRL algorithm say we have robots and we have a pre-trained agent, or it can be any local planner. And when we want to run it in the environment, we take a map of the environment with a one-time setup, we sample, and then we connect only edges that this stochastic controller can consistently navigate through. And basically what that ends up as with a probabilistic roadmap that's tuned to the abilities of the controller, and it won't connect the points that the robot cannot do, which is good. But it is not inefficient because the samples are just random samples, and we end up with lots of zigzag paths and so on. So can we do better than that? So the idea or the intuition here is that environments have some local structure. And by using that, we can learn good samples. And just an example, if I ask you now that you need to, I don't know, go to office or go to a park, odds are you're going to go to the door. If you're in a brand new environment, you've never been before, you're in a conference, never been to that, I don't know, hall before, and you want to go to a restaurant, you're going to go and look for the door. And why you're going to look for the door? Because door is the area that will get you to a position where you can explore more, get you to the larger space. And it's also feasible to you. You're not going to go look for a window because windows are not conducive to you to your control policy. And doors and these kind of what we call them critical samples are samples that are locally recognizable. You look at them, when you see a door, you know it's a door, right? So can we find these critical samples? And the idea how we go about that is then to practice this roadmap navigation with imperfect policies, observe waypoints and their importance within in correlation with our neighborhood, then train a predictive model that takes the neighborhood of a sample or a point and predicts its importance, and then use that to get better probabilistic roadmaps as hubs. So in the example here is we use the PRMs to build for several environments. Here, like this is a Googleplex 4 buildings there. And just use the PRMRL or with the straight line planner. It doesn't matter. And then we practice the queries. Quite a big question here is how to identify critical states. And we use the concept from the between centrality. And basically what we do is that for each node, for each sample there that it's in a probabilistic roadmap, we count how many times we traverse to that. So that's a good thing, right? We want samples that we visit often. Second thing is if we remove that sample, does the connectivity of the space breaks? If it breaks, this sample is important and we need to keep it, right? So that's how we compute the criticality of each node. And then we connect basically the 5 by 5 meter neighborhood and say, okay, this neighborhood, and here the point is in the middle, this is the score. That's our data set. From that data set, we train a neural network that predicts, okay, here's neighborhood, tell me what the criticality is. And how do we use that? So in a brand new environment, never seen it before, we randomly sample. For each of the nodes, we say, hey, how critical this is. And this one returns a high score. Purple ones are, yeah, maybe a little bit less. And these here on the sides are really not that important at all. So next step is then that these samples that are not critical, we can discard a bunch of them. But we do keep the critical ones. And once we start connecting the roadmap, we connect the critical ones globally to any sample that's kind of remained. And these not critical ones, we just connect locally to within the radius. and so on. So basically we end up with this hierarchical roadmap with a lot less nodes that's needed. And then once we just traverse that like normally would. So how does it look like? It really results in orders of magnitude speedups because the roadmaps are smaller and we have these global connections. And it goes across different spaces. What we also notice that the position of the critical nodes depends on the local planner. So if we're using we're using straight line planner versus a planner that's able to avoid obstacles and whatnot, they'll be slightly differently positioned, which is really nice interaction here to see. So in the real world example of the PRMs, we use this for training, and we see that basically hallways are recognized as very critical, which is very intuitively, and then placed on brand new environments it hadn't seen them before. We'll also see that it actually recognizes hallways and narrow passages as important points in the middle of the building, and these in a corner, not really as much. And this is precisely what we want to see. And once this is placed on robot, what ends up being is the motion, the end motion is much faster. Here, the uniform PRM has a point here that the robot can't quite meet example, so it needs to kind of do a roundabout and try it again, whereas the critical PRM has fewer points and fewer failure modes to begin with. So that's exciting. The next example I want to go over is the visual navigation. And here we want to again select a sub-goal. So the idea is that for real world navigation, visual cameras are really important or good. So the visual camera is important to be able to do, and navigation around humans is also important. Training on robot navigation around humans is tricky. It's a safety issue, it's a privacy issue, and so on. If we train this in simulation, we have a question of sim to real gap and photorealism and so on. But then we open ourselves to kind of be able to actually manipulate the data set of humans and make it more diverse and so on. So how do we go about that? Again, we want to end policies to work in the unknown environments before real environments. So we have to go with a simulation, and we merge two data sets. One is the surreal data set of humans that is placed in the Stanford large-scale 3D indoor spaces, basically the data set with buildings. And we're just superimposing humans. And not only that, but we also make humans parameterizable. So we can control their gender. We can control their texture, which involves clothing, skin color, facial features. We can control or parameterize their body shape, whether they're tall, short, and so on, and either moving, how they're moving, how fast they're going, which direction, and so on. So this way we can basically, and then we can render that. So top-down view, this blue one is a robot, human is in red. When we render this, looks like a 3D. There is a human placed in the environment, and then there's a depth image as well. And we call this human active navigation dataset. It's open source, you can find it. And we can use that for training the agents. And we're avoiding the privacy issues, we're avoiding safety issues, and so on. So here are examples of some examples, how humans are placed in this data set and what they look like. And you can find a website here for it. Okay, so how do we train then? One, we practice. So we build a simulation environment and randomly generate and place humans, their initial poses and goals, and solve this with MPC. It's expensive, it takes time, it requires privileged knowledge, but fine, we have it. The second, taking an input image that the robot sees and the waypoint, and basically in this case, like any waypoint that's given, we can predict how we can predict the cost predictor that came out of the MPC. And we train that model. And then when it's time to plan, basically we have the robot, and then you can sample a bunch of points like we did there with the critical samples, or as you would do in RRT. And then for each of these candidate points, we can use the predictor with respect to the MPC. And once we have that, we can select the cheapest one and just drive with it. And that ends up with a zero-shot scene to real transfer, with kind of solving these privacy and safety concerns. So let's see how well it does. In first example here, that red line is what happens when the human is moving, and the dashed line is what happens when the human is static. Purple is human, direction is where the human is moving. So when the human is static, the robot goes in front of it. This is the top image. When the human is moving, the robot goes behind it as expected. And this is really nice. And it seems like the only thing that basically it learns to associate is the position of the legs. And when there's looks like a step, the robot takes a hint that that means the human is moving in that direction and is going to go behind the human. In the second example is the baseline. Baseline is the same method, but trained without humans present on the scene. And that's a dashed line. We see that it basically gets into collision and cuts the person off. Whereas the red line, this is the proposed method, gets here, notices the human is moving and goes behind the human. We also notice that there is, even though we train it only with a single human in the scene, that the robot is able to handle motion between two humans and kind of within. Here we have two humans superimposed in the environment. And here is on-robot experiments. The human is going around behind and goes back. There we go. In the second example, and I should say here in the experiments, when we were looking in training, the camera had 60 degrees angle, and on robot it's only 45-degree angle, which is why we see these kind of low wide turns as well. Okay, so visual navigation around humans. We find the model-based planning that learns to navigate around humans and learns to reason about the human dynamics and dynamic nature of the humans, and generalizes to real-world setting within new buildings and new humans and so on. And then the last example that I want to go over, so the navigation about humans was about we're controlling the robot, human is doing whatever the human is doing, and then the robot is avoiding it. The last example I want to talk is the multi-agent approach, or the cooperative task, where we have two robots or two agents. One can be the human or so on. We're doing cooperative tasks. So there they want to rendezvous. We want the method to be able to transfer again to new environments, real environments. And we're only controlling a single robot at a time. It has access to its own first-person noisy sensor information and can observe where the teammate is. And it has its own this point-to-point control policy that can avoid obstacles, right? And the other robot as well, or human, is controlled by some policy, but that is privileged information that we don't have access. So the only thing that we have access is what we can observe. So we want to find a method that is basically single robot planning in a multi-agent setting that, that solves the cooperative rendezvous task. So one thing that's very important is, can we learn the causality? So if I'm trying to do a cooperative task, I need to know how well I would do in assuming that I have a goal. I also need to know how my teammate will do in achieving that same goal, if we're going to have the same goal. So can we learn to associate current sensor inputs and propose goals and where each of the robots on the scene is going to be in time delta t? That way we can kind of assess the quality of goals that were, or intermediate goals that we're proposing, in order to select the best one. So model, we call this model FI. It's my model from the multi-agent community. Model FI is model that predicts behaviors of all other teammates. So we want to know where the teammates be, and based on what they will observe at that time. And the way we train this, we take an environment. This is again in simulation. We randomly placed obstacles, and we randomly place the robots in goals, and nobody knows where the goals are. And then we let the robots, using whatever policies they have, go reach the goals. At the end of that, then we say, hey, okay, now that I have a whole trajectory here, the hindsight is 2020. Can I take my current observations, where kind of what the world looked like at the beginning? I can assume that wherever the robot ended up being, that's what the goal was. So this is like this is what I see. This is where I think it's going, and then can I predict where it's going to be in time delta t? And that is observed for basically rolling out the trajectories that we observed here in training. And that's how we train these models. Do they train? Yeah, they do, actually. They're, again, not perfect. And self-prediction, predicting where I'm going to be based on my own sensors. Oh, there is not a wall behind me, and so on, is more accurate, has lower loss than predicting where the other agent is going to be, because it depends on the point of view and so on. But this seems to be reasonable. So how do we use it? Doing a joint or planning, we propose a bunch of goals. The initial goal is going to be right in the middle between the two robots. Then we can use our learn model to basically roll out how I and the other agent are going to be, is this feasible for them? So this point is not feasible, right? This point, yeah, it might be feasible. So let's kind of going towards that. But as we're going, we start kind of producing better and better policies, and that's how we end up meeting in the middle. So how does it work? The blue line is the proposed method. Red line is the centralized, which we basically mean that we are training all of them planning together, which is not scalable with the number of as the team size grows. And then the other ones are central. Well, yellow one is centralized as well, and so on. And we actually find that compared to the centralized baseline, we're just kind of competitive with it. And let's see how it works. And this is done in simulation. We had on robot experiments, but this is brought to you by COVID in simulation, their meeting. The centralized actually end up in a local minima, where both of them are kind of staying in the same distance but chasing each other. This is RT, that again, coming into the local minima. And then this is the last one of the examples that in this world, yeah, they meet, and then the centralized baseline again ends up in a local minima. All right, so we went through 4 examples. The idea was to address some of the shortcomings of the motion planning, where it's open loop system and we are not using the previous experience, and construct motion planning where we can get better over time, right? And self-supervision, the reason I'm calling self-supervision is because we can roll out the policy, we can observe the metric as we're going, and they build the models, right? So they learn safety, behavioral models, and producing the sub-goals within the abilities of the controller. And we do that in 3 steps, right? We practice the skills with whatever the best pipeline we have at the time. We collect the data, we train the model, use that for the planning, and keep going and going. And this way we end up with a planning that improves with data and experience and bakes in both controllers, abilities or shortcomings, and compensates also for the sensors and perception shortcomings as well. So some takeaways from here is that model quality depends on data. And there is growing interest and movement in machine learning community to actually invest more in high quality data. And I can't emphasize this enough, that we can use expensive methods, privileged information, computational geometry, and so on to get high quality data. And we should proactively seek easily obtainable data, whether that's the programmable humans, right, or computational geometry methods and so on. And it's really time well spent to get that, because the model's quality depends more on data than neural network architecture, hyperparameters, losses, and whatnot. Second point is environments have local structure, and we generally historically have not used that much. We're just scratching the surface here with kind of localizations and so on, but in different scales and whatnot. Offices are similar, rooms in homes are similar to some extent, but they're different in other extents, and so on. Being able to kind of use that for generalization in motion planning is a big potential here. And then third one is, again, in these kind of settings, looking at the experiences, seeking out causality and learning causality, connecting what happened at the beginning at time t with what the outcomes were at time t plus n, whether something was feasible, doable, easy, how much did it cost, and so on. It's all about predicting future, but it ends up being a self-supervision based on the prior experience. And I think if we kind of continue merging these methods together, we can close the loop and end up with much, much easier planning and controls and robotics that actually works in unstructured environments in real world. And with that, I would very much like to thank you for the time, and I'd like to thank my collaborators. Here's the list of the papers, and this was joint work with Claire Tomlin's lab and Bayer, and now in Tristic was X at the time And with that, if you have questions, let me know. Thank you.